Prediction of trabecular bone anisotropy from quantitative computer tomography using supervised learning and novel morphometric feature descriptors. Osteoporosis is a skeletal disorder which can be assessed by patient-specific finite element models. These models are mainly built using bone morphometry, local bone mineral density, and trabecular bone anisotropy. Bone morphometry and bone mineral density are directly available from clinical QCT scans, while trabecular bone anisotropy is derived from high-resolution QCT scans. In clinics, high-resolution scans are only available for the peripheral skeleton, and not for the axial skeleton, such as the proximal femur. In this slide, a QCT and an HRP QCT image of human proximal femur are shown. The zoomed region shows that the trabecular bone anisotropy is visible on HRP QCT and not clearly discernible in QCT. The aim of the present study is to predict the trabecular bone anisotropy from clinical QCT images using supervised learning. The machine learning approach has two phases, a training phase and a testing phase. The training phase is presented in this slide. From the QCT image, two types of features are extracted, morphometric features and texture-based features. These features are the inputs to the model. From the HRP QCT image, the tensors are computed. These form the output response of the model. A multi-output extra tree regression model is then built from this training data. In testing, the input features of a new case are applied to the trained model, and the tensors for that case are then predicted. For the extraction of morphometric features, an internal coordinate system is constructed based on discovered key points. The coordinate system and the key points are presented in this slide. The 9 morphometric features computed are presented in this slide. The texture features used to train the model are based on first-order statistics and gray-level congruence matrices. On these features, feature redundancy and dimensionality reduction is performed using feature pooling and PCA analysis. The tensors are extracted from the trabecular region using a mean intercept length technique. The tensors lie on a Riemannian manifold. Since Euclidean operations are to be performed, logs of tensors are taken and used. The evaluation was performed on a database of 30 femurs. Example images of the femurs are presented here to show variation in the database. Three evaluation metrics were used for evaluation. They are the tensor norm error, the error in the degree of anisotropy, and the angular error of principal tensor direction. A leave one out strategy was followed for performing numerical evaluation. Error metrics reveal that morphometric features are good predictors of trabecular bone anisotropy. When combined with texture-based features, performance is even better. Error metrics reveal that the proposed approach performs better than an approach based on PLS, and performs comparably to approaches based on registration. However, registration-based approaches are computationally expensive. Our study shows the potential of statistical approaches in the prediction of trabecular bone anisotropy. The approach is registration-free and computationally less expensive. The tensor structure is preserved by the use of multi-output regression. Our results show that computed morphometric features are good predictors of trabecular bone anisotropy.